Hello, ladies and gentlemen. I hope everyone is doing fine in the middle of a pandemic. My name is Kai, and I'm a former undergrad research assistant at the Ohio State University's Automation and Optimization Lab. It's my honor working on motion planning and task allocation for a team of jumping rovers with my advisor Dr. Dai and lab mates who are Yunjin Jung, Isaac Xu, and Chang Huang Wan. Before I begin, I would like to give my audience an overview of this presentation. First, I will present the main motivation, objectives, and problem statement of this research. The motion planning process consists of two steps. I will explain how every path segment is generated and demonstrate the path optimization procedure. Moreover, two rovers with different jumping capabilities were built as an experimental test bed to verify the performance of the path planning and task allocation algorithm. Then simulation and experimental results will be compared and presented. Finally, I will conclude my results and present some future work. As humanity discovers more about the universe we live in, the variety of technologies available to explore unfamiliar terrain has dramatically increased. For instance, sending a nuclear-powered rover to Mars to examine uncharted territory within a tight budget without putting humans in harm's way clearly proven the art and distinction of robotics system. Despite the robotics system's achievement on planetary exploration missions, there are still several limitations to explore rugged environments like cliffs, canyons, and caves due to its massive size and limited locomotion. However, if rovers have an ability to jump on top of an obstacle or over a gap, the jumping capability can provide more degree of freedom on path planning. Additionally, operating a team of jumping rovers can eventually achieve a larger coverage of areas to explore in a shorter amount of time and improve endurance of the robotic system. The main purpose of this research is to develop an energy-efficient robotic system with a cooperative team of jumping rovers that have both rolling and jumping capabilities to solve multiple traveling salesman problems by minimizing the energy consumption of rovers. In order to perform motion planning and task allocation for a team of jumping rovers, a path planning tool called Refined Rapidly Exploring Random Star (RT Star) that was developed specifically for motion planning of a jumping rover will be used to plan paths between any two targets. Then mixed integer linear programming (MILP) will be used to allocate tasks like visiting target points to a jumping rover team with a given objective function and several mathematical constraints that will be discussed in later slides. Before I present the path planning algorithm, let me first define the problem of this research. As is illustrated in the figure, we have m number of targets. Targets can be located on top of an obstacle, and each target must be only visited once by an UGV. And there are n number of obstacles with known dimensions. All obstacles are rectangular shaped and have different elevations. Finally, there are p number of vehicles and each rover can jump at different heights. As each rover has a different jumping capability, the energy cost of each rover is the sum of rolling motion energy consumption, jumping motion energy consumption, and passive energy consumption. While rovers are visiting assigned targets, the jumping rover team should select the path with minimal energy consumption. Therefore, we need to minimize total energy consumption for all rovers during the mission window. This objective function is a product of the cost of each segment and associated binary variable representing selected visiting age. The cost of each segment will be calculated with the refined RRT star process, and the binary variables will be determined by the MILP solver. For calculating the cost of each segment, we need to define how we make the rovers travel from one target to another. Then we utilize RRT star procedures with 1000 samples and 500mm neighbor radius. However, results from RRT star need to be refined to eliminate unnecessary vertices to reduce the cost of each segment. To generate a smoother path, we randomly choose one of the points at the edge and connect them to remove vertices. Next, we eliminated redundant vertices from the initial target to the final target. For a jumping path, the obstacle will be considered as traversable terrain and calculated the cost with the same procedure. Finally, we calculate the cost of each segment based on the vehicle's power consumption characteristics and the number of the jumping motion for the certain path segment. After we determine the path segment between all targets, we need to determine the visiting sequence to search for an energy optimal path, and we can consider this problem as multiple traveling salesman problem, which is known as mTSP. To solve the mTSP with the energy consumption model, a mathematical objective function was formulated to minimize the total energy consumption along with several mathematical constraints. The first two constraints are to ensure only p number of vehicles return and exit from the depot, which is target 1. The third and fourth constraints are to ensure only one UGV enters and exits each target. The fifth constraint is to ensure there is no subtour and it must be complete closed loop for each rover. The sixth constraint is to ensure the same rover visits and departs from a target. The last inequality is the jumping height constraints to ensure the rover can jump on top of an obstacle. For a rover to be used in this simulation, there are multiple requirements. First, it must be able to jump and roll. Second, they must be able to record power consumption and position data in real time to validate the proposed algorithm. Rover 1 was built with Raspberry Pi Zero-W microprocessor that consists of Wi-Fi functionality and commercial off-the-shelf jumping mechanism from Parrot Jumping Sumo. On the other hand, Rover 2 was built with Arduino microcontroller, Synapse serial communication component, and customized jumping mechanism. Rover 1 was built with a lower rolling speed and a higher jumping capability that requires greater power consumption to jump on top of an obstacle that has a higher elevation. On the contrary, Rover 2 was designed for improved endurance and maneuverability, hence Rover 2 has a higher rolling speed, lower power consumption, and lower jumping capability. Based on the power consumption characteristics of each rover, we simulated with two cases. One is to avoid every obstacle and another is to jump over all obstacles lie on the trajectory. According to the generated mTSP solutions for scenario 1, there are two important takeaways from this slide. First, refined RRT stars helps to save a significant amount of energy cost for both jumping and avoidance cases. Second, it shows that with the help of the jumping mechanism, it successfully saves energy by 92% and reduces the completion time of visiting tasks by 5 seconds. For the next scenario, we include one more rover and made obstacle covers one of the targets. The generated mTSP solutions for scenario 2 once again presents that refined RRT star contributes to saving a huge amount of energy cost for both jumping and avoidance cases. Furthermore, with the help of the jumping mechanism, it reduces energy consumption by 178% and decreases the completion time of visiting tasks by 9 seconds. After the simulation, we need to verify the actual energy consumption performance of the rovers. The graph on your right is the experimental power consumption for both rovers. It shows that jumping rover 1 consumed more energy than jumping rover 2 overall. The graph on the left shows the comparison between the experimental and simulation 3D trajectories. Overall, the experimental and simulation results are matched and it just has around 2.6% error. Here's the experimental demonstration. In conclusion, the results from virtual simulation and physical experiments have demonstrated the improved performance of using the jumping capability to follow the path from the solution of the mTSP with obstacles and effectiveness of the proposed motion planning and task allocation method. In the future, we hope to improve the control jumping capability to optimize the jumping motion energy consumption for a certain height of an object. Besides that, we also hope to investigate the use of multiple jumping rovers with a solar charging station rover to improve the sustainability of the robotics system. Lastly, we also wanted to expand to a larger and more diverse group of drones such as a team of unmanned aerial vehicles and unmanned ground vehicles. Thank you.